Lesson 4, we'll be talking about two things, arc length and area of a surface. We will first be talking about arc length. I put this little blurb in here that has the two formulas for arc length, but first let's just talk about what that means. Example 1, find the arc length of the graph on this interval. You all don't have this little graph on your note sheet, but I just dropped that in there. That's a graph of that function. Here's 1/2 on the x-axis, there's 2. So what we're finding in this problem is the length of this piece, how the length of the graph between 1/2 and 2. There's two formulas for the arc length of a curve. It depends on if your function is a function of x or if your function is a function of y. Depending on which one you have, that determines which formula you will be using. And the formulas are essentially the same, it's just that one has x in it and one has y in it. In our case, we have a function of x. You know that because you look at the function and you see x's in the function. You see y equals with x's in the function. Our a and our b are 1/2 and 2 respectively because that's the interval that we are interested in finding the arc length over. So looking at what we need here, I need to take an integral of a square root of 1 plus the derivative squared. So I will need the derivative of this function. This f of x is just like our y, our function. So I'm going to start off by taking y prime. And before I do that, I'm just going to rewrite y. I'm going to rewrite y as 1/6 x cubed plus 1/2 x to the negative 1. And now I will go in and I will take the derivative of that. Y prime, bring down the 3, new exponent on x is 2. Bring down the negative 1, new exponent on x is negative 2. So again, be careful here, y'all. We're taking derivatives, not integrals. So I know we've spent a lot of time doing integration, but we have to be able to know the difference between derivatives and integrals and what we're doing when. So I'm going to go ahead and just simplify this derivative. This is a 1/2 x squared minus 1/2 x squared. And to make this even a little bit more simpler for what we're going to be using it for, I'm going to go ahead and factor a 1/2 out of this. So that leaves me with an x squared in the first term. And in the second term, it leaves me with a 1/x squared because this x squared right here was in the bottom. So I have y prime. I will need to square y prime. This here says that we will have to square our derivative. And so I'm going to take y prime and I'm going to square it. So I'm going to take 1/2 x squared minus 1/x squared, and I'm going to be multiplying it by itself. I'll just multiply the 1/2s first. That's going to give me a 1/4. So I've taken care of the two 1/2s, and now I'm just going to FOIL these two pieces out. X squared times x squared is x to the 4th. X squared times 1/x squared is a negative 1. Okay, so let me write this. Make sure it's clear what I'm doing and where I'm getting these expressions from. X squared times x squared has given me x to the 4th. X squared times negative 1/x squared gives me a negative 1. Negative 1/x squared times x squared gives me another negative 1. And then negative 1/x squared times negative 1/x squared gives me a positive 1/x to the 4th. Okay, so now I have that all multiplied out. I will combine some like terms in here to get 1/4. Move this over. To get 1/4 x to the 4th minus 2 plus 1/x to the 4th. So I have the derivative squared. So I have everything that's circled in red. So I have this part, f prime squared. We took our derivative and our squared it. We have this. I will need to add 1 to that and stick it under a square root. So I'm going to just go ahead and do that. So notice I have not done an integral yet. Right now we're really just doing, we took a derivative and we've been doing a bunch of algebra to simplify things. So I'm going to come in and do what is 1 plus y prime squared. So I'll add a 1 to the expression that we just had. And now remember, all this is going under a square root and it's being simplified. So let us simplify this sum. So we will have the like term. We can combine the 1 with the number that we would get after we distributed the 1/4 to the -2. Distributing the 1/4 to the -2 would give us a -1/2. And then adding 1 to -1/2 would give us a +1. So you don't have to write this down if you're following what I'm saying, but if you're not, in other words, what I'm saying is I'm distributing the 1/4 right now. So this would be a -1/2 plus 1/4x to the 4th. And I'm not going to leave it like this because I want it in the form that I had it before, but you'll see why. I'll explain why I'm doing this in a second. So now I'm going to combine these two like terms. 1/2 minus 1 is 1/2. So I have 1/4 x to the 4th plus 1/2 plus 1/4x to the 4th. So you have that expression there. And I'm going to factor a 1/4 out of this. I'll explain why I'm doing that in a second. I know it might not seem like it makes much sense now. I also don't think I gave you all that much room for this problem. I'm sorry about that. Okay, let's pull out the 1/4. When you pull out a 1/4, you're dividing everything by 1/4. So you're multiplying everything by 4. So this is just the x to the 4th that we're left with. This is a +2 that we are left with. Be careful with your algebra there. And then this is just a 1/x to the 4th that we're left with. Yeah, I definitely didn't give y'all enough room. That's my fault. So what we have here is now everything under the square root. It's everything under the square root because we have taken 1 plus the derivative squared. So now let's look at what the square root of that expression is. I'm going to go off to the side here. So I'm going to be taking the square root of 1/4 x to the 4th plus 2 plus 1/x to the 4th. Let's go ahead and just break that up into the square root of the 1/4 and then the square root of everything else. Square root of 1/4 is 1/2. And this is the part where it gets a little tricky with algebra-wise. Taking the square root of this trinomial here with these 3 terms being added. That's not reading the trinomial because, anyways, taking the square root of these 3 things being added together. In order to do that, we need to first rewrite, which is see how it's going to happen, rewrite what's under here as something squared. And if I can rewrite what's under that square root as something squared, then it'll be very easy to take the square root because the square and the square root will cancel each other out. So what we're going to be doing basically is we're going to be factoring that weird expression that's under that square root. Okay, so the first term of this must be x squared because it is by squaring x squared that you're able to get x to the 4th. And the last term of this needs to be 1/x squared because it is by squaring 1/x squared that you get 1/x to the 4th. We have not yet checked on whether or not we will get that 2, but we would. If we were to FOIL out what I just wrote in green, we would get x to the 4th plus 1 plus 1 plus 1/x to the 4th. And those 2 1s together come together to give us that 2 right there. Generally speaking, once you have that expression of what's under the square root simplified like we do here, what's underlined in green, once you have that simplified, everything that's circled in blue there, oh man, everything that's circled in blue there, the logic that I just used on how I came up with x squared and how I came up with 1/x squared, seeing what I had to square to get this and what I had to square to get that, and then checking that I did get my 2 in the middle, that will pretty much always work for simplifying that. And the reason that we wanted to write it like that is because now the squared and the square root will cancel each other out, and we'll just be left with 1/2 x squared plus 1/x squared. Okay. And remember, all of this is what's on the inside of the integral, and we did take the square root of it, so we're good with that. So now the problem becomes, yeah, I definitely didn't give y'all enough room, I'm so sorry. So now what does the problem become? Now the problem becomes, I'll erase this. I'll just write the formula up here. I'm just going to use y prime squared instead of f prime squared since we had a y in our function, our problem. We know a and b is 1/2 and 1. That's coming from here. So we have the integral from 1/2 to 1 of this whole square root of 1 plus the derivative squared. We have done all of this work here to simplify that down to this. We took the square root, there's the square root right there, of 1 plus the derivative squared. We took the square root of all that stuff and we simplified it to get that blue cloud at the bottom. So that's what I'm putting on the inside of the integral. 1/2 x squared plus 1 over x squared dx. I don't need that parenthesis right there. I'm going to go ahead and pull the 1/2 out in front of the integral. And now we can start integrating. Notice that I did rewrite that last term as x to the negative 2 instead of leaving it as 1 over x squared. So I have 1/2, integrate x squared to get x cubed over 3. Integrate x to the negative 2, increase your exponent up to x to the negative 1 and divide by your new exponent. So you're dividing by a negative 1, which is really just going to make that term negative. And then this is evaluated from 1/2 to 1. Be careful with this 1/2 that's out in the front. It is multiplied by everything that we're going to be getting here because it was in front of the entire integral. So first I'll plug in my upper limit of 1. And I'll just rewrite this x to the negative 1 as 1 over x. Upper limit of 1 gives me 1/3 minus 1. Subtract, plugging in my lower limit of 1/2. 1/2 cubed is 1/8. That's over 3 minus 1 over 1/2 is 2. I could really just write it like that though. 1 over 1/2. That's 2. And now I'm going to put all of this in my calculator and hit math enter to give me 33 over 16. So that is the length of this piece right here on that graph. It's the length of that piece there. Okay, let's look at another example. So I just took this over off to the side because we're not going to have enough space there. Again, I'm sorry about that. There's some information missing here. This should say find the arc length of the graph on the interval from 0 to 8. And we're going to round to 3 decimal places. Okay, so let's see. This function is not given to us in terms of y or in terms of x. Like it's not solved for y and it's not solved for x. So let's see which one. We could solve for either one. One may work, one may not, we'll see. And that will determine which version of the formula we're going to be using, either the ones with the x's or the ones with the y's. So if I tried to solve for y in this equation, I would be cube rooting both sides of the equation or taking both sides to the 1/3 power. Same thing, so 1/3 power up here, 1/3 power up there. The 3 and the 1/3 here would cancel and just leave me with y minus 1. And then on the other side of the equation, I would have x to the 2/3. So now I'm going to add 1 to both sides of the equation to get y is equal to x to the 2/3 plus 1. Now, we have to be careful with this version here because this derivative is not defined when x is equal to 0. This might seem unfamiliar to you. We talked about this when undefined when x is equal to 0. We talked about this back in Calc 1, but if we were to look at the graph, and I'll pull the graph up really quickly. If we were to look at the graph of x to the 2/3 plus 1, we're going to see a cusp at 0. So what I mean by a cusp is this. That's what the graph looks like. That little corner, that little pointy part right there, that's a problem when we're dealing with derivatives. The function is not differentiable right there. If we were to take the derivative of this function, we would end up with x in the denominator, and we can't have 0 in the denominator. So that's why we're seeing that issue right there. So it's undefined when x is 0, but 0 is included in the interval that we're looking at. So we cannot use this version of the function because it is undefined. So it did not work for us when we solved for y. Instead, we need to go in and try to solve for x. So I'm going to take the same equation, y minus 1 cubed is equal to x squared. I'll square root both sides. So I'm taking both sides to the 1/2 power now. So this is getting an exponent of 1/2 and this is getting an exponent of 1/2. And the only reason I'm writing it like that instead of square rooting it is because I want you all to have the correct exponent on it, and I want you to have this. I want you to have this. Right. From multiplying the 3 and the 1/2. So we have y minus 1 raised to the 3/2 is equal to x. Ooh, and plus or minus this, right? Plus or minus, because we do have to do plus or minus whenever we take a square root. We're going to choose the plus because all of the interval that we're looking at for the arc length over it has all positive x values. So we get the x is just equal to y minus 1 raised to the 3/2 power. So now that we have our equation solved for x, now we will go in and we will take the derivative. So we have the function, we have x as a function of y. We solved for x, y is showing up in our function. So now we are looking at this version here. So like that right there is like our x prime. We need to take the derivative of what x is. So I'm not taking dy dx, I'm taking dx dy, x prime. So we will bring down the exponent of 3/2, keep the y minus 1. The new exponent is a 1/2 because we do 3/2 minus 1. So we have that derivative there. We do need to square this derivative, and so I am going to square it. I'll multiply the 3/2 together first to give me a 9/4, and then I'll multiply I did this the long way. I could have just squared both the terms. The y minus 1 together, and with the y minus 1 to the 1/2 multiplied with the y minus 1 to the 1/2 will just give us a y minus 1. So we have the derivative squared. Now I'm going to see what is the derivative squared when I add 1 to it, because remember, part of what we have to do is we have to take the derivative, square it, and then we have to add 1. And then we will go in and put that under the square root. So again, these problems start off with a lot of algebra. You could write the whole thing from the beginning, like the whole setup, but I don't think that's very intuitive, and there's not really much you can do because you do still have to go through all this algebra to get to where you're trying to go. So 1 plus the derivative squared would be 1 plus 9/4 multiplied by y minus 1. I'm going to go ahead and distribute that 9/4 just so I can get this 1 pushed in. So I have 1 plus 9/4 y minus 9/4. And 1 and a negative 9/4 is going to give me a negative 5/4. So I have 9/4 y minus 5/4. And I will go ahead and factor a 1/4 out of this. I said I would tell you why I did that in the first example, and I'm not sure that I did. But just to make the point clear, the reason that I pulled this 1/4 out is that once we got under the square root, it's very easy to take the square root of 1/4. So things that are definitely perfect squares, I have them by themselves factored out so that when we get to that square root, we can just take the square root of that. Same thing's going to happen with this 1/4 that I have pulled out right there. So everything that we have right here is now going to be going under the square root. All of this. So I need the square root of 1 plus the derivative squared. So I'm now taking the square root of 1/4 9y minus 5. And now you can see that the square root of 1/4 is 1/2. So I have 1/2. And that 9y minus 5 is supposed to stay under the square root. So this is what's inside the integral. Again, we have done all of this algebra, all of this work, just to figure out what is inside of the integral. Okay, so now that we know what's on the inside of the integral, let's go set our integral up. What we need to talk about what the limits will be, the c and the d. Now it's very tempting to say that the limits will be 0 and 8 because this is the interval that we're working on here, but these are x values. And things did not work for us when we tried to write the function as a function of x. We had to switch over and write it as a function of y. So we cannot put x values on our integral. We need to put y values on our integral. So I need to figure out what is y when x is 0 and what is y when x is 8. Well, we had solved for y right here. I did cross it out because it did not work for us in terms of differentiability. It was, it's not undefined. That's not the right word. It's not differentiable when x is equal to 0. But that is what y is equal to. So I'm going to make a quick little table here for x and y and see, well, when x is 0, what's y? And when x is 8, what's y? When x is 0, so I'm plugging into the red box the fact that y is equal to x to the 2/3 plus 1. When x is 0, y is 0 to the 2/3 plus 1, which is just 1. And when x is 8, y is 8 to the 2/3 plus 1, which is 5. So 1 and 5 are the limits on our integral. So now I can set the integral up. So I have the integral from 1 to 5. And again, we did this whole table and did this whole switch because we are putting things with y on the inside of the integral. Everything has to match. The limits, what's on the inside of the integral, and the dy at the end. 1/2 square root of 9y minus 5 dy. I'm going to go ahead and pull the 1/2 out of the integral. And then we're going to integrate this 9y minus 5. So I'm going to let u equal 9y minus 5. Then du is 9 dy. But we don't have a 9 dy. So 1/9 du is equal to dy. We could switch limits here, but I'm not going to. I'm just going to do this integration off to the side, and then I'll go and plug in what we have. So the integral of 9y minus 5 dy is 1/9 the integral of u to the 1/2 du. So I'll increase the exponent on u up to 3/2 and divide by the new exponent. So I'm taking 1/9 and I'm multiplying it by 2/3. I'll just put a plus c here for now. So I have 2/27, 9y minus 5 raised to the 3/2 plus c. So I did that off to the side because that gives us what the integral is. So I still have the 1/2 out in front. When we integrate, this is what we will get. So I'll put a 2/27 right here. And then this 9y minus 5 raised to the 3/2 power needs to be evaluated from 1 to 5. Those 2's cancel. I'm left with a 1/27 on the outside. I'll first plug in 5. 9 times 5 is 45. 45 minus 5 is 40. Raised to the 3/2 power. Then I'll plug in 1. 9 times 1 is 9. Minus 5 is 4. So then I am subtracting 4 to the 3/2 power. So this here is our exact answer. 1/27 times this 40 to the 3/2 minus 4 to the 3/2. And then rounding that to 3 decimal places gives us approximately 9.073. So that is our final answer. Okay, on to our third example. Find the arc length. We have a curve. We have 2 x values that we want to stay in between. I will just write off to the side here. We will integrate this from a to b and take the square root of 1 plus y prime squared dx. It might be dx, it might be dy. We'll see what's going to happen as we get into it. So let's start off by taking the derivative. So I need to know what y prime is. We have natural log of cosine x. Quick reminder, there is a rule that tells us the derivative of natural log u is u prime over u. In our case, u is cosine x. The derivative of cosine is negative sine x. So u prime over u is negative sine x over cosine x, which is a negative tangent x. It's a quotient identity from 172. So we have y prime. Let's go ahead and square y prime and add 1 to it. We don't, by the way, we don't have any issues. We don't have to worry about things not being differentiable on the interval like we did the last time, because tangent is going to be continuous until x is 0. Yeah, tangent will be continuous until we get to pi over 2. So we definitely are on an interval where our function will be differentiable. The derivative does exist. Okay, so I'm going to go ahead and start setting the whole integral up here. This one's going to shake out a little bit. You know what? I'll just stay consistent with what we've been doing. Y prime squared is squaring a negative tangent to get a positive tangent squared. And then 1 plus y prime squared is 1 plus tan squared x. So that's what's going under our square root. So we have the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. Now, how do we integrate this? We have to use a Pythagorean identity to simplify it some more. 1 plus tangent squared is equal to secant squared. All of that right there is equal to this, which is very convenient because now it makes it very easy for us to take the square root of that. The square root of secant squared is simply secant. So we have the integral of secant here, and the integral of secant, we had a trig, not a trig, we had an integral rule for that. Let me go find that and pull that up and show it. Okay, so it took me a while, and it's not less than 29 because this numbering is off. At least I don't think it's less than 29 because the numbering is off. I wonder if I can see what it is on WebAssign real quick. No, I can't. But the lesson that we had on integration of natural log, example 8 tells us here, use the fact that blah, blah, blah to show that secant x is equal to that. So secant x being equal to natural log, the integral of secant x being equal to natural log of the absolute value of secant x plus tan x plus c is an integration rule that we will know and use now because that's what we're integrating. We are now integrating secant. So the integral of secant is natural log of the absolute value of secant x plus tan x. And we will evaluate this from 0 to pi over 4. So I will first plug in pi over 4. We have natural log absolute value of secant pi over 4 plus tan pi over 4. And then from that we are subtracting natural log absolute value of secant 0 plus tangent 0. And so now let us evaluate some things. Secant of pi over 4 is root 2. Tangent of pi over 4 is 1. So we don't really need the absolute value bars anymore because this is a positive number, so we don't have to write that. Minus natural log of secant of 0 is 1, and tangent of 0 is 0. And natural log of 1 is 0. Ln of 1 is equal to 0. So all this equals this here. Natural log of the square root of 2 plus 1, which is approximately 0.881. So the second half of lesson 4 is talking about the area of a surface of revolution. So all that means is, imagine that we have this curve here that I'm outlining here in black, this curve on that graph. If I were to rotate that curve around the x-axis, not talking about the 3D figure per se. Well, you could think about the 3D figure that it would make. It would make a figure that looked like that. But what we're going to be finding here is the surface area of that figure. So all of the area along the surface, the outer surface of that figure. Again, we have two different formulas depending on whether we have a function of x or whether we have a function of y. This formula looks very similar to the previous formula that we had for the arc length, but one thing that is new is we have this r of x or r of y, depending on which variable we're using, on the inside of the integral, and that r represents the distance between the graph and the axis of revolution. Same thing down here, it is the distance between the graph and the axis of revolution. So let's look at an example of how we will apply that formula. Example 4, you want to find the area of the surface formed by revolving the graph of y is equal to x cubed on the interval 0 to 1 about the x-axis. So first, I'm just going to sketch a little graph of what that looks like. So first, I'm going to sketch the big picture, and then I'll kind of readjust the graph. So the graph of x cubed looks like that. That's what x cubed looks like. Let's say that this right here is where 1 is. So we're only dealing with this part of the function, so I'm going to erase everything else. That's just the graph of x cubed between 0 and 1. Revolving around the x-axis, we're going to see something that kind of looks like that. And I'll show you a picture of what the whole 3D figure would kind of look like. It would kind of look like that. So you can see this is the piece of the graph that I drew, and then I came in and drew that right there. So you can kind of see like this 3D figure that we're seeing looks kind of like a spinning top. So we're finding the surface area of that figure. Okay. So we do have our function f of x equal to x cubed. That is a function of x. First, I will just write down the formula that we will be using. The formula is that the surface area is equal to 2 pi, the integral from a to b of r of x multiplied by the square root of 1 plus, the formula says f prime, I'm just going to write y prime squared dx. So let's start finding the pieces that we need. Our a and our b are going to be 0 and 1 respectively. A is 0 and b is 1, and I know that because we're working on this interval from 0 to 1, and we will be working with x values here. The function was given to us in terms of x. We have no differentiability issues with this polynomial, x to the third. It's continuous and differentiable everywhere. Y prime, taking the derivative, is 3x squared, and I'll go ahead and I will square my derivative to give me 9x to the fourth. So square the 3 and square the x squared. So far all we have missing left is r of x. And remember that r of x is the distance between the graph and the axis of revolution. So r of x would be whatever this distance is here, the distance between the blue graph and the axis of revolution, which is the x-axis. And that distance is just the height of the function, which is x cubed. How tall that is, it depends on what x is. It's going up and hitting the function, it is x cubed. You could also think of it as top minus bottom. The top is the function, x cubed. The bottom is the x-axis, our axis of revolution. So we are ending up with x cubed there. So now that we have everything that we need, let's go ahead and set up our integral. We will have the s is equal to 2 pi, the integral from 0 to 1 of x cubed times the square root of 1 plus 9x to the fourth dx. So I've plugged in all of the pieces of information that we had into our formula. So now we need to integrate. We can integrate this simply using u substitution. I'm going to let u be 1 plus 9x to the fourth. Then my du is 36x cubed dx. We don't have a 36 on the inside of our integral, so I will divide both sides by 36 to get that 1 over 36 du is equal to x cubed dx. So now we're ready to go in and start doing some substitution and some integration. I'm not going to change, I don't think I've changed limits at all today in this lesson. So let's go ahead and try this and we will go ahead and change limits. So I have 2 pi, the integral. I'm going to leave those limits blank for now. This x cubed dx is getting picked up by a 1 over 36 du. So I have put the 36 in the denominator out in front of the integral, and I put my du at the back. What's left on the inside of the integral is the square root of that 1 plus 9x to the fourth, and that was our u. So inside the integral, we have u to the 1/2. What I'm going to go and find now are the new limits, because the original limits are written in terms of x, and now we have done a substitution with u. We had x limits of 0 and 1. Plug them into what u is equal to, which is 1 plus 9x to the fourth, to find new limits. When we plug in 0, we will get out 1. When we plug in 1, we will get out 10. So our new lower limit is 1 and our new upper limit is 10. So now we're ready to integrate. I'll keep this pi over 18, just simplifying the 2 and the 36 there. Integrating u to the 1/2. exponent goes up to 3/2, divide by 3/2, so we're multiplying by 2/3, and we will evaluate this from 1 to 10. I'm going to simplify this stuff right here first. So we have 2 becomes a 1 and 18 becomes a 9. We have pi over 27 multiplied by 10 to the 3/2. I'm applying fundamental theorem of calculus now, minus 1 to the 3/2. 1 to the 3/2 is just 1, so we don't have to put that 1 there. So this is our exact answer for that area, surface area, which is approximately 3.563. And there's our approximation. For our last example, similar problem, we will be finding the area of the surface formed by revolving the graph of y is equal to x squared on the interval 0 to √2 about the y-axis. So y is equal to x squared kind of looks like this. Let's say that √2 is right here. So we're only working from 0 to √2. We're only working with this blue piece of the function, and this time we're revolving around the y-axis. So we're going to end up seeing a surface that looks kind of like a bowl, and I'll show you a picture of that surface. That surface looks like this. So this is a little piece of the curve that we drew, x squared between 0 and √2, and then we're revolving around the y-axis so we can see this bowl shape that we're seeing here. So again, I will just start off and write the formula. So S is equal to, switch colors, 2 pi integral from a to b. We're again working with x here. We don't have any issues with the function not being differentiable or continuous on that interval. It's a polynomial, it's continuous everywhere, and the function was already given to us in terms of x, and that's going to work for us. We don't have any issues with that, so we'll just stick with that. So we have r of x, square root of 1 plus y prime, which needs to be squared, dx. So let's start identifying things. Our a is 0 and our b is the square root of 2. It's coming from the interval that we're working over. Our y was x squared. We already have that. So our y prime is 2x. I'll go ahead and square y prime to get 4x squared. Make sure you square the 2 and square the x. And then we also need to know our r of x. R of x is the distance from the axis of revolution to the curve, to the function. Distance of the graph, distance between the graph and the axis of revolution. So this red distance here, that would be our r of x. Now, that distance there, remember this is going and this is hitting y is equal to x squared. That is a horizontal distance. Whatever that horizontal distance is the x value of where that function is hitting the curve. And it's a positive, it's a distance. It's an x value. So we have the equation y is equal to x squared, but this distance is x. So I'm going to square root both sides to get that y is the square root of x. And notice I did not put plus or minus because, to get that y is x. Square root both sides to get that y is x. Notice I did not put plus or minus because we're talking about a distance here. And so our r of x is equal to x. When you're finding your r of x, it's very important that you remember it is the distance between the function and the axis of revolution. That could be the x-axis or that could be the y-axis. I'll just mention, side note here, if we were doing this problem and going around the x-axis, if we were revolving around the x-axis, this would have been our r of x, this green distance here, which would have been the height of the function. It goes up to the function. Then it would have been x squared. But that's not what we're doing. We're not revolving around the x-axis like we did in the last example. Okay, so now that we have everything that we need, we're ready to go ahead and start setting up our integral. So we have s is equal to 2 pi. Integral from 0 to √2 of x. There's our r of x multiplied by the square root of 1 plus 4x squared dx. We can again integrate this with u substitution. So I will say that u is 1 plus 4x squared. Du is 8x dx. We do not have an 8 in our integral, so I will divide both sides by 8. 1x du is x dx. I'm going to do the same thing I did last time, and I'm going to be changing my limits. So I'll just go ahead and make a little table over here. X and u. We started off with x limits of 0 and root 2. U is equal to 1 plus 4x squared. When x is 0, u is 1. And when x is root 2, we have 1 plus 4 times root 2 squared. Root 2 squared is 2. So that's 1 plus 4 times 2, which is 9. So our new limits on the integral will be from 1 to 9. So we have 2 pi. I'm doing the substitution now. Integral, new limits from 1 to 9. This x dx is getting picked up by 1/8 du. So I'll put a du at the end and an 8 in the denominator on the outside. And then the square root of 1 plus 4x squared, that is u to the 1/2 power. And now we're ready to integrate. So I'm going to go ahead and simplify this 2 and this over 8 to a pi over 4. Increase the exponent on 1/2 up to 3/2. Divide by 3/2, which is multiplying by 2/3. And then we will evaluate this from 1 to 9. I'm going to just simplify here. That becomes a 1, that becomes a 2. So I have pi over 6. Multiply the 2 and the 3. Plug in the upper limit of 9. Plug in the lower limit of 1. 1 to the 3/2 is still just 1, so we do not have to do anything with that. 9 to the 3/2 power is 27. So we have pi over 6 times 27 minus 1, which is pi over 6 times 26. And then I'll simplify to leave me with 13 pi over 3, because 2 goes into both of these. That's our exact answer, and our approximation to 3 decimal places would be 13.614.